This video will present the work done in the scope of a semester project at the CREATE Lab of EPFL studying backdrivable actuators applied to tendon-driven robotics. A test setup is assembled using a computer vision system. A camera is tracking a robotag fixed at the end of the robotic arm. This maps its position in 2D space. There are two motors in the system. The first motor, at the bottom, the base of the arm, is actuating the arm from the inside, pulling on both tendons through a pulley with two different diameters. The second motor is attached to the outside of the structure and pulls on the arm through a load cell to characterize the properties of the arm when it's being flexed with or without a motor attached to its base. This will enable us to determine the backdrivability of the motor chosen to actuate this solution. In addition, fiberglass rods can be added inside of the arms as struts used to rigidify the system from 2.5 to 6 millimeters in diameter. The first experiment is conducted. It consists in estimating the required torque needed for the motor to flex the arm across its entire workspace. For this, a digital dynamometer is attached to the rightmost tendon and a 2 kilogram weight attached to the left tendon. The dynamometer is pulled progressively from 0 to 250 newtons, and the position of the arm is mapped using the computer vision system. We find that the arm behaves very similarly to a torsion spring, with spring coefficients dependent on the thickness of the rod added inside of the arm. We can then use this spring constant to estimate the needed torque of the motor. The second study is conducted. It consists of finding the path across 2D space taken by the end of the arm when pulled from 0 to 250 newtons, depending on the diameter of the rod added inside of it. The results are very interesting, as we find that for rods under or equal to 3 millimeters in diameter, the arm actually flexes more than when pulled with no rods inside of it. For rods 4 millimeters in diameter and above, the arm acts more like a rigid beam and flexes less. The third experiment consists of backdriving the arm through the load cell, firstly with no motor attached to its base and with varying thicknesses of rods. We find once again that the thicker the rods, the more the arm is difficult to actuate, but the results get really interesting when we start adding motors to it. In the second part of the test, we add motors to the base of the arm and backdrive it again from the load cell pulled by the external motor. Here, we find that the torque curve is less linear, as we have to first break the rotor inertia of the motor and then backdrive the motor in addition to the arm. But the really interesting tests come when we subtract the blue curve from all the other curves and look at the sole impact of the motors on the backdriving force curve. We find that the dynamical motor is similar in terms of steady-state backdriving resistance to the brushless DC Maxim motor with a reduction of 103 to 1. The Maxim motor with a reduction of 243 to 1 is much higher in backdriving resistance at about 3 times. But what is really interesting is to compare these values when they've been factored out for motor peak torque. By looking at this parameter, we find that the Maxim motor with a 103 to 1 ratio has a better steady-state resistance to peak torque than the Dynamixel. Another very interesting parameter to look at is the rotor inertia of the motor that we can estimate by looking at the first hump before the motor arrives in steady-state resistance. We find that the Dynamixel motor has almost no hump, so it's very linear when we start pulling on it and when it breaks loose, but the Maxim 103 to 1 reduction has a large hump that overshoots and then gets back to steady state mode. We estimate this to be due to the compound planetary gear head used by the Maxim motors, which stick a lot and need to break all the gears around the planets, unlike Dynamixel, who uses staggered spur gears, which probably break one after the other linearly. The fourth test consists of estimating the filtering effects of the soft TPU robotic arm on the torque bandwidth curve of the motor. For this, we actuate the arm in a sinusoidal manner from 0.2 Hz to 20 Hz in 0.1 Hz increments from 0.2 to 1 and 1 Hz increments from 1 to 20. we find that the data is very noisy as the camera is mounted on a pole which resonates with the arm. But as a very unscientific test, from 0.2 to 5 Hz, the arm nearly perfectly respects the control input given by the motor. From 5 to 10 Hz, the control input is less and less precise, and above 10 to 15 Hz, the control input is almost unrecognizable. Therefore, we can estimate that the arm behaves like a first-order low-pass filter with a frequency cutoff around 10 Hz. Overall, we find that the data is satisfactory and enables us to first spec out the required torque of a motor. They also make us consider not only the rotor inertia, but also the gearbox stiction and the steady-state resistance of the motor. We also realize that torque bandwidth is hard to measure, but any input under 5 Hz should go through the arm. And finally, I would like to thank the entire CREATE Lab for their help all semester long, notably Professor Josie Hugh, Dr. Francesco Stella, Andrea Perone, for all the help that they have brought to me throughout the semester. And as always, this was made with love by Loïc.